We have been talking about solutions, and we've been talking about how to make them and how to measure their concentration. And now in this lecture with colligative properties, we're looking at how is a solvent different when it's in a solution than when it's not in the solution. What happens to things like melting point, boiling point, electrical conductivity, things of that nature. So this is looking at how the properties of a solution change because of dissolved solvent. So here we go. Take a moment and write that. So colligative properties are about how a solution changes because it's got this solute in it, how a solvent is different than a solution with regard to various measurable properties. The overarching, nutshell, say it in one sentence, answer to colligative properties is that the solution likes to be a liquid. That's the general answer to all of these things. So when you compare a solvent and a solution, generally speaking, a solution has a lower vapor pressure, which means fewer of the particles of solvent are leaving the liquid state and finding themselves above the liquid as a gas. And that goes along with the overarching thing that in a solution, the liquid wants to stay a liquid longer. Less of it is running away out of the liquid and becoming a gas, a vapor. So lower vapor pressure, okay? Higher boiling point. Again, it likes itself more. A solution has higher intermolecular attractions than a pure solvent. And so you can add more thermal energy to that solution, and it's vibrating faster, vibrating harder, but inside it likes itself more. So it can be at a higher temperature and still be a liquid, okay? A higher boiling point in a solution versus a pure solvent, okay? And then a lower freezing point. It likes to be a liquid longer. So you can lower the temperature and the particles stop vibrating as much. They slow down in their thermal energy, but they don't freeze right away. Okay, so this is why you add salt to boiling water if you're cooking noodles. Anybody pasta people, right? Or even the Chinese noodles, same idea. You want to salt the water before you cook it. The reason you salt the water is that raises the boiling point. And so instead of cooking at 100 degrees Celsius, you're cooking your noodles at 105. And so it cooks your noodles hotter, which allows them to be done sooner. That's why you salt the water, right? This is why if anybody's ever lived anywhere that had ice and snow problems on the road, you salt your driveway, or you salt the street, or you salt the sidewalk, because that lowers the freezing point, and now all of a sudden the ice and snow that was ice and snow becomes liquid water. It melts, and you're not heating anything up. It's still, 12 degrees outside or whatever, but when you throw salt on the ice, now 12 degrees is liquid, and so it all melts, and you can broom it away or shovel it away a lot easier than solid ice. So adding salt to water raises the boiling point, cooks your food faster. Adding salt to ice melts the ice. Because generally speaking, solutions would rather be liquids than any other state. Okay? Generally, do you understand the idea? Lower vapor pressure, higher boiling point, lower freezing point. And if you just remember, it wants to be a liquid. All of those will make sense to you. Okay? So here is a comparison of a pure solvent and a solution. And this is the phase diagram. So again, this is pressure and this is temperature. In here, in this region, bounded by the purple line, is where the pure solvent would have been a liquid. Outside of this, it would be a solid and a gas. But we add solute to it and we turn it into a solution, and you can see that in the blue line, where the solution is, there's a bigger region of the graph where it's a liquid. It becomes a solid at a colder temperature. It becomes a liquid, a gas at a higher boiling point. Okay, So the region where it becomes a liquid is more where it exists as a liquid expands on the graph in a solution versus the pure solvent. Okay, take a second. So these changes are related to the number of particles dissolved in the solution. The more solute particles there are, the more these changes are expressed. So the higher the boiling point, the lower the freezing point. Depends on how rich the solution is. So we've already talked about molality, and molality again is the moles of solute per kilogram of solvent. And so that's the one we're going to use for calculating the amount of boiling point elevation or freezing point suppression. Okay, and we're going to take into account how many particles or ions a solute dissolves into when it's put into water. So think about a sugar molecule. It's all covalently bonded. You dump sugar in, and the sugar crystals will break up into individual sugar molecules. How many particles of sugar molecules there are is directly related to how many moles of sugar you put in. All the sugar dissociates, but it dissociates in just one molecule at a time. So the number of particles, the I, is just one. A sugar molecule is a sugar molecule, and if it's dissolved in water, it's still a sugar molecule. But that's different than salt. You take salt, sodium chloride, it's in crystals. You dump those crystals in the water, the crystals dissolve. They go into solution, but it doesn't stay one sodium and one chlorine hanging out together in solution. The sodium and the chlorine dissociate. And so for every one molecule of salt, NaCl, you actually have two particles in the water, two things, because the sodium and the chlorine are ionic, and they disassociate from each other. And so ionic things actually become separate particles when they're dissolved in the water, not still sodium chloride, but a sodium ion surrounded by water molecules and a chlorine ion surrounded by water molecules. So if it's a covalently bonded thing, I is 1. But if there's an ionic bond in there that will separate, then we have to count the number of things that it will separate into. So sodium chloride separates into 2 things. But if you were to do something, I'm just going to try to pick an example like magnesium chloride, MgCl2, and we were to dump that in water, the magnesium and the chlorine would separate, and the 2 chlorines would become separate ions, and the magnesium would become a separate ion. So you'd actually have 3 particles that dissociated from each other when you dissolved in the water. So we have to look at the molecule and say, okay, let's break everything that's ionic up. How many things, how many pieces of this will there be? If it's all covalent, I is 1. If it's ionic, you need to look and count. How many ions will there be? So that's that number. And then there's this thing called a mole constant, and that is unique to each solvent. So the solvent responds in a certain way to things dissolved in it, and you'll just need to look up what K is. What is the value for K for this particular solvent? It'll be in a table in your book, right? So you'll need to look that value up, and then the molal concentration you need to know. And again, that's moles per kilogram. And so when you put all this together, you wind up with this equation. The change in temperature is equal to the number of particles that this thing dissociates into times the constant for the particular solvent you're talking about times the molality. Okay? When I learned this in school, I learned the M in front, and it was Mike. So the change in temperature is Mike's fault, is how I remembered it. It's Mike's fault. The temperature changed, M-I-K, molality, number of particles, and the constant. But your book expresses it in this order. I think it's still easy to remember that the change in temperature is Mike's fault. So that might help you. But I just wanted to keep it the same way that your book expresses it. So IKM, the number of particles times the constant times the molality will give you how many degrees Celsius the boiling point goes up, and the freezing point goes down. Okay? So let's do an example question here. 30 grams of salt is added to 1 liter exactly of water. At which temperature will this solution boil? Okay, 30 grams of salt exactly and 1.00 liters of water. So I don't have moles yet of salt. I need to get to moles of salt. So I need to do a little bit of stoichiometry to figure out how many moles of salt I have. So we're going to gather some information from a table. For water, the value of K is 1.86, and you just need to look that up. The molar mass of salt, NaCl, 58.44 grams per mole. And the density of water, so I can get my mass of solute, is 1 gram per milliliter or 1 kilogram per liter. So I know that my 1.00 liters is in fact 1.00 kilograms. Salt dissolves into 2 ions, right? Na and Cl, they will split up into 2 things when they get into water. So now I can put all this together. I need my molality, moles of solute per kilogram of solvent. We have 30 grams of salt, and the molar mass is 58.44 grams, so I need to do a little division and find out that I have 0.51335, too many significant digits, but we'll leave it there for now. 0.51335 moles of solute. Molality, 1 liter of solvent, which is 1 kilogram. So 0.51335 moles per 1 kilogram, because molality is moles per kilogram. So my molality is 0.51335 molal. Okay, so my value for I is 2. My value for K is 1.86. My value for M is 0.51335. Now I can do my equation, right? 2 ions, 1.86 for K, 0.51335 molal. So I will do my multiplication, and I find out that the change in temperature is 1.90966 degrees Celsius. So that's not the temperature at which it boils. That's really stinking cold, 1.9, right? But this is the change in temperature. So this is how much the boiling point went up and how much the freezing point goes down. So I can now use that to answer my question. I have to do significant figures, right? 1.91. So the question is, at which temperature will the solution boil? The change in temperature is 1.91 degrees Celsius. Let me move my beautiful face out of the way. There you go. Since water normally boils at 100 degrees Celsius, we would expect the solution to boil at 100 plus the 1.91, because this is a change in temperature we just calculated. So it should boil at 101.91 degrees Celsius. So adding 30 grams of salt to 1 liter of water only raises the temperature almost 2 degrees. Okay, so it goes from boiling at 100 to boiling at 101.91 degrees. So if you want to cook your pasta at 105, 110, you've got to add a truckload of salt. You've got to add a lot of salt. If you just put a little bit of salt in your hand and dump it in the water, you really haven't done anything to it, right? And if you live somewhere cold in the snow and you want to melt the ice and you just sprinkle a little bit of salt, that doesn't do much. You got to salt, and then okay. Okay. I'll let you actually take a moment to write this down. Osmosis is what happens when diffusion can't. So if you were to take a highly concentrated salt solution and a much less concentrated solution, maybe even pure water, you take these 2 volumes of water and you separate them by a semi-permeable membrane that lets water move through, but does not let salt move through. Now the salt wants to spread out. The salt wants to go from a dense solution across into a not dense solution. But every time the salt tries to spread out past the barrier, it bounces off the barrier. The barrier doesn't let the salt through. So you have this imbalance. And nature abhors an imbalance. It wants everything to be balanced. So the way to balance those two solutions is, if the salt can't move, is the water will move. And the pure water from one side, or the lower concentrated salt solution from one side, will move through the barrier to dissolve the salt over here and lower the concentration in the densely concentrated solution. So if you have two volumes of water that start off as the same volume, and you put in a semi-permeable membrane, and you dump a bunch of salt on one side and stir it up, now the salt can't go over, you'll actually see the water level go like this. And this membrane will let water go through. So you're like, wow, that's weird. There's more water over here. And it's not like spilling through into this side. And that's because the water from the pure water is going through the membrane to lower the concentration of salt on the side that is densely concentrated. And the more water that happens over here, the lower the concentration. And it'll keep moving until they are at equal concentration, until this water has gone down enough that the concentration has gone up on one side, and this water has gone up enough so the concentration is the same on the other. And so that pressure, that push that moves water across the membrane, we call osmotic pressure. And we say water wants to move. Water doesn't have a will. It doesn't want anything. But the two solutions will pass water back and forth until they are at the same concentration. So this is kind of cool to see when you see the water level rise and drop. And you're like, ooh, that's weird. But we also use it quite a lot. We use this sort of thing in food processing. You will sometimes see that vegetables come packed in water, and the reason for that is that the pure water outside the vegetable goes inside the vegetable to dissolve the stuff in the vegetable, and it makes the vegetable stay wet and crispy and full of water and not saggy and limp and nasty. And so, that's a little trick. If you ever bring celery or carrot sticks for lunch, put them in some Tupperware with some water, and they'll be crispier when you have them later on. And so we use it that way. Also, this same sort of principle is used in making decaffeinated coffee. The water goes into the bean and displaces the caffeine a little bit, and then they remove the caffeine that comes out. Anyway, a little bit more complicated, but it's the same sort of water motion process that they use to make decaffeinated coffee. So you will see this in a couple of applications in your life where water moves into something and changes its concentration to balance concentrations. This is also why if you're in the bath for a long time, you get pruny fingers, right? Same sort of reason is there's stuff in your cells that can't leave your cells and go into the bath water. But the bath water can go into your cells. So you get all puffy in your fingers as the water is trying to dissolve you, right? It's the same reason. So osmotic pressure. I have some pictures here for you showing that example. So there is sugar on one side of a semi-permeable membrane and not on the other. And then the water from the pure side goes through the semi-permeable membrane to dissolve the sugar. And the water volume over there drops, and the water volume on the other side rises. Okay, and that is because of osmotic pressure. There was a superhero named Osmosis Jones, right? Or a cartoon character of some kind. It was a movie. How was he at all tied to osmosis? Did he?
He was a cop in the body, so I don't know.
I don't know how that tied in, but there you go. Oh, sorry. So there's another way to get something inside something else. The solutions that we've been talking about this whole time are when a dissolved particle is truly dissolved. It's in the solution, and the solvent molecules totally surround it, and it is happy, and it will stay that way forever. It will never settle out. If you have salt water, the salt stays in the water. The salt doesn't settle out. You don't go to the bottom of the ocean and find this layer of salt that has settled out of solution and is sitting on the bottom of the ocean. That would be really weird if you found that. The salt stays in the ocean, and so that's a solution. But there are some examples of things where you can get it to quote-unquote dissolve for a short amount of time, but eventually it does settle out. And so those things are not solutions. If it settles, it's not a solution. If it settles, we call it a suspension. And we still use the word colloidal, like colligative, and that has to do with being, intertwined. But it's a suspension, not a solution. And there's a big difference between them. A suspension tends to be opaque. It scatters light. Whereas solutions tend to be clear, or at least translucent. You can see light that travels through them. They behave differently as far as conductivity and all those sorts of things. And so because a solution and a suspension are fundamentally different sorts of critters, we use different terminology for them. So we talk about a solute being dissolved in a solution. But if we're talking about a suspension, we don't use the word solute because we want people to know that this is not a solution that we're talking about, that this is a suspension. And so we use the word dispersed particle, or the words dispersed particle. These are the things that are scattered out. They're not dissolved, they're scattered out. Okay, they're dispersed. And the majority component that we would call a solvent, if it had dissolved the stuff, we call a dispersing medium. It's the thing that has stuff scattered through it. So the dispersing medium and the dispersed particle is the suspension version of the terminology for solute and solvent. Okay? And I'll show you some pictures as to why these are different sorts of things. This cup of joe, you can see here that there is gas in the frothed milk, but it's not dissolved. Like, there's a difference there, and given time, these bubbles will find their way to the surface and go away. They won't stay there for all time and eternity, right? And then in the coffee, there's some milk here, and the milk is quote-unquote dissolved, but not really. Given enough time, coffee and milk will separate, and you'll have a layer of milk and a layer of black coffee. You don't want to drink it at that point, because by that time the milk has gone nasty. But it will happen over time, right? And so because it will eventually settle out, this is not a solution. This is not a solution. These are suspensions. Okay, and so one thing is dispersed or scattered in something else. Here we have smoke in the air. This is a suspension. We have particles of ash and particles of wood and particles of all kinds of stuff coming off of fire, going up into the air, and it's not dissolved in the air because several miles away, this stuff will settle down out of the air and become a layer of ash on somebody's driveway. And so it's not dissolved in the air, it's suspended in the air. It will eventually settle out, it doesn't stay there forever. And then the easiest way to distinguish a suspension from a solution is to shine light through it. Here I have a solution, and here I have a suspension. As the light travels through the solution, it goes through uninhibited. It doesn't scatter. You don't see pieces of the light beam coming out somewhere else. But when it goes through the suspension, you see the beam of light, and the reason you see the beam of light is because it's being scattered out and hitting your eye, or in this case, the camera taking the picture. And so a suspension scatters light. A solution, the light tends to go through with no problem. Okay, so it's an easy test to see, is this a solution or a suspension? That page 320 was the old version of your book. Let me see if it still is the right page. So that's page 328, sorry. So many kinds of colloidal suspensions are very familiar to you, and we just saw some examples of them. Coffee is a suspension, soda is a suspension. You can have solids dispersed in a gas, and we call that smoke. So in, over a fire, obviously, or sometimes electronics get too hot and the capacitors pop and smoke. Anytime you have smoke, that's a solid that is being dispersed into a gas. Liquids dispersed into a gas are aerosols. Ladies in the morning, if you use hairspray, looks like there's a look around the room, not a whole lot of hairspray users. But that is a liquid in a gas that comes out of the can. Or a cloud is liquid water dispersed in a gas. And then gas dispersed in a liquid, the other way around, is foam. So shaving cream is a liquid dispersing medium that has gas dispersed in it. So there's lots of them. There's other examples of that on page 328 in your book. You can see multiple examples of common colloidal suspensions. Here are some of them, okay? Gases cannot dissolve a gas. I'm sorry, gases cannot disperse within a gas. They're all mutually miscible, so they don't form a colloid, but they form solutions all the time. But again, if a liquid is dispersed into a gas, we call that an aerosol. If a solid is dispersed into a gas, we call that a solid aerosol. Smoke is an example of that. And then lots of these are in your book. You don't have to write these down. But a liquid dispersed in another liquid is an emulsion. Milk is an emulsion. A solid dispersed in a liquid is a sol, S-O-L. Paint is that. Blood, you are largely that. And then a solid dispersed in another solid is a solid sol, and that is colored glasses. The colored glass is an example of that. Anytime you take two solids and mash them up into a fine powder, that's an example of that. So solid foams, gels, emulsions, liquid foams. These are all examples of colloidal suspensions where one thing is not really dissolved in the other. They're just dispersed amongst each other. But there's no dissolving going on. And that is it. Any questions?